So I'm going to go over each question that's on the practice test, and so you'll know how to approach each one. First of all, there's a couple of questions on there that deal with just the definition of a limit. In other words, the delta epsilon definition. And there are a couple of ways I can get at, do you understand that definition? And one is by giving you a limit and giving you an epsilon and asking you to find the corresponding delta. Because remember, with limits, what we're saying is, as you box in, like if we say the limit is x goes to 2 of x squared equals 4, what that means is, if I go up here to this 4 and I box it in, go a little above and a little below, no matter how small I make that little box in, no matter how tight I make this little interval in here, I can go back down here, trace back down to the x-axis, and get an interval about this 2, so that everything in the interval down here will give me a function value in the interval up here. In other words, for every epsilon, no matter what epsilon I choose, I can always find a delta down here. So no matter how small the epsilon neighborhood is up here, no matter how close I am to 4 up here, I can find a corresponding delta neighborhood so that every x in this neighborhood will give me a function value up in this neighborhood. So here I have epsilon is 1. That means I go up here to 4 and I add 1 and I subtract 1. So this is 4 plus 1 epsilon. This is 4 minus 1 epsilon. And then we trace that back down. That 5 corresponds to the square root of 5 on the x-axis, and the 3 corresponds to the square root of 3. So I want to use the smaller of these. So I'm going to say delta equals the minimum of the square root of 5 minus 2, and the other one 2 minus the square root of 3. We pick the smaller of those, and we'll say, okay, that is our delta. And we know that any x value we pick in here is guaranteed to give you a function value in the epsilon neighborhood up here. So that's what we do with these. Now, on the practice test, I gave you several just for, so you could get practice. But you can see we do the same thing. As x goes to 2 of x cubed equals 8, same process. Same process. Okay, I'm just going to trace the 9 back down. See, epsilon is 1. 2 cubed is 8. I go up 1 to the 9, go down 1 to the 7, and trace those back down to the x-axis. Here's the cube root of 7, cube root of 9. And then I pick the smaller distance, from 2 to the cube root of 9 or from 2 to the cube root of 7. And then, of course, I've given you the other one with the square root function. Same process. So this is the way that when I'm trying to assess if you understand what a limit is, this is one of the ways that I can ask a question. Giving you an epsilon and having you find the delta. Yeah. Okay. Now, let's look at another way I can talk about the definition of a limit. Remember, if we say this, here's the deal. If we say the limit as x goes to a of f of x equals some limit. When we say that, and you need to be able to state the definition, what does this mean? The limit as x goes to a of f of x equals a. Here's what that means. For all epsilon greater than 0. All of them, no matter how small you pick epsilon, for all of them, we can find a delta greater than 0. In other words, for a neighborhood of on the y-axis, we can find a neighborhood on the x-axis such that this implies this. In other words, if x is in this epsilon neighborhood, then f of x will be in the, if x is in the delta neighborhood, then f of x will be in the epsilon neighborhood. So if x is in the delta neighborhood, then f of x is in the epsilon neighborhood. Okay? So to explore that, we could do these proofs. We could say, okay, let's prove using this idea that this limit is true. Well, I'm going to start off with this part, f of x minus L less than epsilon. So I'm going to do f of x, let me do absolute value, f of x, there it is, minus L. Now, that's less than epsilon. But I'm not going to write that yet. I'm just going to say, well, let me go ahead and simplify this a little bit. Go ahead and do the math inside here. This is 2x minus 6. Okay, I can also factor out a 2 here. Okay, now, here's the deal. Once we get to this point right here, remember this is f of x minus epsilon, f of x minus epsilon, f of x minus epsilon. f of x minus L, f of x minus L, f of x minus L. Now when we get to this point right here, let's go ahead and put the minus epsilon. Now when I say this point right here, I mean when I get to this x minus this number right here, this a. See? X minus a. See the a there. So x minus 3. And then just divide by the 2, and look what we've got. Now, if you think about it, what we've just discovered here is that if I just choose delta to be epsilon over 2, that fits in with this definition of what the limit is. In other words, I started off with f of x minus L, went through this process, this line here, and came to the point where I could say, oh, well, notice I've got x minus 3. So if I just let delta be epsilon over 2, that proves the limit. That's all we need to do is just we need to find a delta. And we can find a delta no matter what epsilon you give me. I just say, well, divide it by 2 and you've got it. Okay. So that's another way we can talk about the definition of the limit, or the meaning of this, what this means. We start off with f of x minus L, and it comes through, and we end up with x minus a less than something. And that something we'll call the delta. Now, that process there, sometimes that takes a little bit of time to soak in and say, well, how does that prove it? So you got to think about it. Sometimes it requires a little thought. You reflect on what's going on here. But anyway, now you've got another one here, which if anyone would like, I can go back and do that one. But we go over the same process. It's exactly the same way. Okay, now the next thing on the study guide was we have these limits that we are evaluating analytically. Now, this first one, okay, it's got this sign in it, okay, the sign of something over x. Now, remember, when you see something like that, you're automatically remembering or thinking about this, that I know that the limit as x goes to 0 of sine x over x, I know that that's equal to 1. So this looks a lot like that. So when you see that, you're thinking about this limit. Now, here's the deal. This is not that, though, because we've got a 3 here. But that's okay, no worries, because we can just multiply the top and the bottom by 3. That's no different than just multiplying by 1. But now, look what happened. We've got sine 3x over 3x. Now that is this. This is sine of something over the same something. Okay? Sine x over x. We've still got this 3 here, so let me just factor that out. So I've got sine 3x over 3x, and that is 3 times 1, which is 3. Now, you can experiment with this a little bit, and you'll find out that going through this process, doing these tricks, you can evaluate a limit like this. Sine ax over bx. By a little bit of work, you can show that that is just a over b. In other words, if you look at this enough and play around with it, you'll see, yeah, okay, that limit's just going to be a over b. And we get that from this basic one. So what I've done here is I've just put some random limits, and so that we have to, each limit we come to, we just have to think about it. In other words, it's not in any particular context. So this was the first one, when I see something like this. Now this one down here, the limit as x goes to 4, x minus 4 over the square root of x minus 2. Okay, now remember, what you try first is to plug in, because sometimes that's all you're going to need to do. If we plug in the 4 here, we get 0, and if we plug in the 4 down here, we get 0 as well. So we get 0 over 0. Now that tells us we need to simplify this in some way. There's a couple of ways we can go about simplifying this. Now we're just going back to our skills, our algebra skills at this point. Now, I'm going to work this problem 2 different ways. One way is I'm going to, and I don't know which way you'll fancy, so I'll just do it both ways. But the first way is I'm going to multiply by the conjugate of this thing down here, and we'll see if that gets us anywhere. Whoops, square root of x minus 2. Okay. So we've got the square root of x minus 2, and I'm going to multiply that by the square root of x plus 2. Okay, I just do that. Now what happens then on the bottom is, let's see here, you're going to get the limit as x goes to 4, and then on the bottom you get x minus 4. See that? And up top here, you get x minus 4 times the square root of x plus 2. Now, right away, you can see what happens here. This cancels. And then I can just plug in, and I get the square root of 4 plus 2, which is 4. So that's a little trick we could use there. Now, that's not the only way we could do this. I could do this. I could say, I could think about this. Let's see here. I'm just going to leave the bottom as the square root of x minus 2. Now I want to rewrite this top. Now notice this is x. Isn't that just the square root of x squared? It is, right? So I could write this as the square root of x minus 2 times the square root of x plus 2. In other words, I could factor this way by viewing this as a difference of squares. In other words, what I'm doing is I'm viewing this as the square root of x squared. See, that's what that is. And then, so if you multiply this out, you get that exact thing back. And notice this cancels, and then I just plug in, and you get 4. So that's a couple of, just some algebra tricks. And a lot of what we do in calculus is just algebra tricks. That's it. Okay, so now let's ease on down here. Uh-oh, look at this. This looks a lot like this celebrity limit up here, this thing. See, that's what jumps out at us. We've got sine 7x here. Oh, I see. Okay, well, let's look here and see what happens. I'm going to take the limit as x goes to 0. And I'll do this. Let me split this up. I'm going to do 3x over 2x. Okay, I'm just splitting it up because I see this sine 7x over 2x. I like that. So let me just split it up that way. Okay, so I've done no harm here. Right? Now, if you look at this first limit right here, the limit as x goes to 0, you can see that these x's will divide out. I mean, you could plug in here and you'd get 0 over 0, but you can see, I can take out those x's. Now, so this is going to be, this first limit here is just going to be 3/2. That's pretty obvious. Okay. Because there's no need to, a lot of times we have to factor and then cancel, but no, we can just see the factors here. So that's 3/2. Now, minus, look at this one, sine 7x over 2x. Well, that's just a over b, right? 7 over 2. See that? So we can make that 7 over 2. Now, we just observed that shortcut. If you wanted to just work through this, you would multiply the top and the bottom by 7, and then the top and the bottom by, the top and the bottom by 7. And then you would factor out that 2, the 7 over 2. See, so in other words, if we wanted to do this the long way, I would just multiply by 7 over 7. And then you could factor out the 7/2, and you would have sine 7x over 7x. Okay, so moving along, and I can go back on any of these, and we can work. I can answer any questions that you have. Now, this one is the greatest integer function, and what I've done is I've sketched the graph of this function over here, and what it says is that when you put a number in here, you're going to evaluate the function as the greatest integer less than or equal to that number. So, for example, 2.1. 2.1 is going to give you a 2. So if you come over here, here's 1, and here's 2. 2.1 is going to give you a 2. 2.3 will give you a 2. 2.4 will give you a 2. But when you get to a 3, it jumps up here to 3. Now, also, you could say negative 2.1. Now, you have to watch yourself on the negatives. You're moving to the left. So if you have negative 2.1, well, that's down here at negative 3. See, it's the greatest integer less than or equal to. So it's the integer to the left. Okay, so you're moving to the left. So if we're talking about this limit right here as x goes to 2, okay, here's 1, here's 2. Now dig this. As we approach from the left, our limit is 1. As we approach from the right, our limit is 2. So the right-hand limit is 2, the left-hand limit is 1. So this limit just does not exist because the left-hand limit and the right-hand limit are different. Okay, because we got jumps, right? Okay, now let's look at this one. We have the limit as x goes to 4 of the absolute value of x minus 4 over x minus 4. Now you try to plug in first, then you get 0 over 0. But think about what this function looks like here. If you put in values bigger than 4, think about this. If x is greater than 4, like let's say 6, well, you have 6 minus 4 over 6 minus 4. Well, that's just 2 over 2, right? Which is 1. Now think about it. If you put in any number bigger than 4, it's going to be equal to 1. On the other hand, if you put in a number less than 4, okay, like, let's say 2. You have 2 minus 4 over 2 minus 4. Well, what you get up top is the absolute value of negative 2, and on the bottom you get negative 2. Well, that's just 2 over negative 2, and that's equal to negative 1. So here's the deal. With this function looks like this. If you were to sketch a graph of it over here at 4, let's say this is 4. What you've got is a function that looks like this, a horizontal line going that way and a horizontal line going that way. And you can see that the right-hand limit is equal to 1. The left-hand limit is equal to 0. So this limit does not exist. Okay. Because right there at 4, you got to jump. So what we're doing is we're looking at these special cases and how to approach them. This is one of them. This greatest integer function is another. Now, look at this one. The limit as x goes to 6 of x minus 5 over x minus 5. Absolute value up top. Well, we plug in. And we get, 1. 1. So that's the limit. Because, seeing this doesn't necessarily mean the limit doesn't exist. The limit wouldn't exist here if this were x goes to 5. But x goes to 6, yeah, that limit exists. On this one up here, the limit exists everywhere but 4. Okay. Okay, mosey along here. Okay. So here's one. The limit as x goes to negative 5, 3 over x plus 5. So we try plugging in and we get 3 over 0. We get a 0 on the bottom. That tells us we've got a vertical asymptote there. Yeah, vertical asymptote. So if you look at this, so we're thinking, okay, this is either going to positive or negative infinity. That's what's happening. So we've got, negative 5 over here. So here's negative 5. Okay, negative 5. There's our vertical asymptote. And if you look at that, the question is, as we go to negative 5 right here, what's happening to the right of this asymptote? Well, it's either going to be going up like this, or it's going to be going down like this, either to positive infinity or negative infinity as we approach from the right. Okay. Now it's just asking what is the limit. Well, as we approach from the right, just plug in numbers to the right, like negative 4. Well, if you plug in a negative 4 up here, you get a positive. So that tells us that it's going to positive infinity over here. Positive infinity. However, if you approach from the left, you're coming this way. Well, what does it look like that way? Well, just plug in a negative 6. You get a negative when you do that. Any number you plug in over here, you get a negative. So that tells you that it's going down like this. Negative infinity. So as you approach from the right, you're going up to positive infinity. As you approach from the left, you're going to negative infinity. So we would just say this limit does not exist. If it had a plus sign there, a little plus, it would be positive infinity. If it had a negative, it would be negative infinity. But it has neither one. It's just asking what is the limit. And we don't know what to say, Depends on which direction you're coming from. So we say, yeah, that limit doesn't exist. They need to be more specific. Which direction? Okay? So, first off, we recognize that. Now, notice, if this had been 0 over 0, we wouldn't have thought vertical asymptote. We would have thought, okay, I need to do something to simplify this, and then plug in again. Okay. Now, look at this one. As x goes to infinity. Now, when we have x going to infinity, what we're concerned about is what's blowing up faster, the bottom or the top? Now, if you look at this, we've got x cubed up here, 3x plus 5. Down here, x cubed, 2x cubed plus 3x. Now, if we didn't have this exponential term in there, the limit would be 1/2. Because the degree on top, degree on the bottom are the same, and we just use the ratio of the leading coefficients. However, these exponents really tend to dominate. We've got this exponent down here, and it's blowing up faster than anything. You've got a polynomial up here, but down here you've got this thing that's growing very quickly, and therefore this limit would be 0. When the bottom is blowing up faster than the top, it's dominating. We say, okay, that limit is 0. Now, if the top had the exponential term in it, it would just be going off to infinity. Okay. So now, let's look at this one. Notice the difference here. Now x is going to negative infinity. Negative infinity. Now, this is the same problem, only we're going in the different direction. We still got the exponential term down here, but you're putting in negative numbers in for x. So what's happening to this 3x? Let's suppose that x is equal to negative 100. What's happening to this 3 to the x? Well, you have 3 to the negative 100. That's equal to 1 over 3 to the 100. That's a very wee number, very small. And it just gets smaller. What if x were negative 1 billion? Well, you'd have 1 over 3 to the billion. Well, that's tiny. So what's happening here is this term is going to 0. It's not amounting to anything. So we're back to looking at the leading coefficients here, which is 1/2. We just look at the ratio of the leading coefficients because that exponential term is going away. So it matters. So the thing is, you have to take each problem and analyze it. Okay. Now, this one. The limit as x goes to infinity. Okay, so we're looking at this. Let's think about, okay, we can just forget about the e for now. Think about what's happening to 1 over x as x goes to infinity. Well, as x gets larger and larger and larger, let's think about that. X, and down here is 1 over x. And here's x is 10, 100, 1,000. Well, think about it. 1 over 10, that's 0.1. 1 over 100, that's 0.01. Here's 0.001. Look what's happening. 1 over x is getting closer and closer to 0. As x gets larger, 10, 100, 1,000, 1 over x is getting closer and closer to 0. So 1 over x is getting closer and closer to 0. That means that e to that is getting closer and closer to e to the 0, which is 1. Yeah. Okay. Now, let's look at this one. Now, when you look at this, your eye might fall on this thing, sin x over something down here, and you might think, oh, I bet that's going to be one of those celebrity limits. However, then your eyes look over and see x is going to infinity, not 0. See, x is not going to 0, it's going to negative infinity. Well, then you shift gears. You're thinking, okay, I'm not thinking then in terms of that celebrity limit. I'm thinking in terms of what's blowing up faster, the top or the bottom. Well, if you look at the top, you've got x to the 5th, and then you've got this thing. Now, this thing right here is oscillating between -2 and 2. So really, it doesn't add much to this. I mean, you've got these numbers being raised to the fifth power plus 2 or negative 2. It does, that's not really making a big contribution. So what you're looking at really is this x to the fifth over x to the sixth. And x to the fifth over x to the sixth, well, the bottom is blowing up faster than the top. You got a bigger power on the bottom. So this limit's just going to be 0. Because you're putting in bigger and bigger numbers, and you've got like negative a billion to the fifth plus 2. You don't care about the plus 2. Negative billion to the sixth. The negative billion to the sixth is bigger than negative a billion to the fifth, right? You don't care about this part right here. Doesn't matter. Okay, now ease on down here. Here we've got some trig over the square root of x. We look over here. X is going to infinity. That puts us in the frame of mind of what's growing faster, the top or the bottom. Well, this top is just 1. So what you've got up top is just a fancy way of saying 1. The bottom is growing faster than 1. 1's not growing at all, so this is just going to be 0. And you wouldn't even have to recognize the top as being 1. You just know, well, sine and cosine, the biggest they can possibly be is 1. So the biggest this top could ever be is 2. I mean, if you were thinking that way, but actually, this sine squared x plus cosine squared x is just 1. Okay. Okay. Now, we look at this one, plug in the 4. Okay. That's always, so when you approach a limit, you're thinking, I'm going to plug in a 4. I plug in and see if it works. If I plug in, I get 0 over 0. So this is just one of those basic ones where the trick is to factor and cancel. So the bottom is pretty easy to factor. Okay, and the top, I think it'd be easy to factor too. We've got negative 4 and negative 3, I guess. Yeah, there we go. Look at that. Then we can plug in. So we got 4 minus 3 over 4 plus 4. So a basic one like that, just factor and cancel. Now this one, we try to plug in and we get 0 over 0, but we notice this is one of those kinds where we have extra denominators, right? So we're going to multiply by the common denominator. That's the trick. Just multiply the top and the bottom by 5 times x plus 1. Or, in other words, multiply every term. And here's what happens. Things cancel. You get rid of those extra denominators. That's the trick with these ones. So let's see what we got here. We got 5 minus, be careful to put it all in parentheses, the x plus 1. And this down here is 5, x plus 1, x minus 4. Now remember, don't fall into the trap of canceling out the x plus 1. That would be nice, but it's wrong because it's connected over here to this 5. You can't just break these two apart. They care too much for each other. So what you have to do is you have to simplify the top, simplify the bottom. Well, really, there's nothing to do on the bottom. In general, you're not going to multiply this out. So what you're going to get is you're going to get 5 minus x plus 1. So that's our minus 1. So that's going to be 4 minus x. There we go, like that. See? 5 minus x minus 1, and you get that. Now notice 4 minus x minus 4, those cancel to give you a negative 1. And then you can just plug in. And it looks like that's going to be negative 1 over 25. Okay, now another trick is in dealing with ones like this. And notice you get 0 over 0. And on these, what we think about is multiplying by the conjugate. Okay, just multiply the top and the bottom by the conjugate. And what you get is, up top, you're going to get 4 plus h minus 4. And on the bottom, you know, I'm not really doing anything to the bottom. There's what we get. See? Because when you multiply a minus b times a plus b, you get the first term squared minus the second term squared. Okay, all those cancel, or those two. And you're left with the limit as h goes to 0. The h's cancel. And now you can just plug in. And you get 1 over 4. Oops, there it goes. 1 over 4. Okay. And here's another one that is just the same way. An extra one there. But I'll go ahead and skip down here. Now, on the so here is a piecewise function. We're asked to evaluate limits. Notice that we're going x equals to 2 from the left, from the right, and then we're looking at the overall limit. When you have this kind of limit, and it says, okay, the limit is x goes to 2 from the left, well, you're going to go up here. You have a choice to plug in here or here. Well, this is the only one where you actually have x values to the left of 2. So you have to plug into this one. See, because this is the one that applies when x is less than or equal to 2. And that's what you have when you're approaching from the left. So this is going to be 3 times 2 plus 7. I was having trouble reading my writing. Yeah, so this is 6 plus 7, which is 13. So that limit's 13. Now on this one, as you're approaching from the right, it's over here. So this is 4 plus 2, which is 6. And this one does not exist because the left-hand limit and the right-hand limit are different. Okay, continuity. It's the next thing we looked at. When you're dealing with continuity, what you want to find points of discontinuity by setting the denominator equal to 0. And here you've got x plus 2, x plus 3. So your points, your places of you have discontinuities at -2 and -3. Those are two places where you have discontinuity. Now your concern is, I wonder if you have a vertical asymptote there. In other words, are these infinite discontinuities or just holes in the graph? Well, you find that out by factoring and seeing if something divides out. Okay, so I've got x plus 2, x plus 3. Now you notice x plus 2 cancels out. That tells you that this is removable. And this, however, does not divide out. So there's a vertical asymptote there. And this is infinite. So you have a removable discontinuity at x equals -2, and infinite at x equals -3. Now down here, you have a piecewise function, and you're trying to determine where the discontinuities are, if there are any. Now, everything happens, you have 2 is kind of the boundary. To the left of 2, you have 2x plus 1. That's continuous every place. 5 is continuous every place, and x squared plus 1 is continuous every place. But when you're transitioning from one of these continuous functions to the other, you might have a discontinuity. So what I do is at this 2, I plug in 2 times 2 plus 1, and that gives me 5. Okay? And of course here is 5 at 2. So at 2 you're at 5. And then I plug in down here 2 squared plus 1. That's 5. So it looks like there's no discontinuity, because right here at 2, when you transition, you go from 5 to 5 to 5. They're all 5. So this one, it hits 2 and it goes up to 2 and it's 5. So there's no discontinuity on that one. However, on this one, let's see. We plug in a 3 and we get 2 times 3 plus 1. That's 7. 3 times 3 plus 2. That's 11. There's a jump discontinuity at x equals 3. Okay, now, one more thing. We've got the graphs. This was pretty much the first thing we did in the class, where you just are evaluating these limits from a graph. And remember, this first one, the limit as x goes to -3, right here, from the left. So if you look up here, that's going to be 5. You just go up, right, until you hit a place where you have graph to the left. And I notice that's 5. Then it says, okay, approach from the right. Well, if I do the same thing, I keep going up until I find graph to the right, I'm up here at 7. These are different. So this limit, as you approach -3, doesn't exist. Now you can come over here, and it says the limit as x goes to 3 from the left. Okay, so here's 3, and it's 5. The right-hand limit is also 5. So this limit is 5. So those are pretty easy. Okay, so we need to be able to look at a graph and know what the limit is. And you can tell where a limit's not going to exist because there's a jump like that. Now, for this one where we're trying to speculate about what the limit is numerically, all that is plugging in. So I plug in a -1 into this function. I plug in a -0.75, a -0.5, and I just look and see, does it look like there's a trend here? And then you speculate. Yeah, I think as you get closer and closer to 0, or as you get closer and closer to 0, I think this limit is 0. Now you could also use the squeeze theorem, because if you think about this, and this is x to the 4th. Okay? In other words, you can find x to the 4th, negative x to the 4th, and x to the 4th. Those two functions, this function is always between those. And you know that this limit right here is 0, and this limit right here is 0. So this one is squeezed in there, and it's also 0. So that's another way to look at that limit. You just figure, and the reason you can say x to the 4th sine 1 over x is between negative x to the 4th and positive x to the 4th is because sine can never be bigger than 1. And it can never be less than -1. So really, this whole thing is boxed between negative x to the fourth and positive x to the fourth.